Hi guys, this is the fourth video on the calculation of expected value. This time we will be calculating the expected value for a standard six-sided die, and the probability of getting any of those six numbers is 0.16667, and we know how to calculate the expected value. See, we have to multiply all the distinct values of the random variable. What is random variable? Random variable is nothing but 1, 2, 3, 4, 5, 6. We call it random because when we roll a die, we don't know which number will appear. That is precisely why it is called random variable. So we will consider each distinct value involved in the random variable and multiply those values with their respective probability. Now here, for each and every number, the probability remains the same. Hence, we are multiplying these numbers by the same probability, that is 0.16667. So here multiplied by 1, here multiplied by 2, 3, 4, 5, 6. And when we do this, we get 3.5. And this figure, this 3.5 is the expected value for a standard six-sided die. Okay, this we did earlier for a coin. This time we are doing for a die. Now, see, the point over here is if we pretend to be rolling a die six times, ideally we should get 1, 2, 3, 4, 5, 6 each time. But that is not going to happen because the numbers will appear randomly. So let us run and see when we are rolling six times what is going to happen. See, we got 1 once, 2 we got twice, 3 we got once, 4 we got once, 5 we got once, 6 we have not got. 6 is missing. Now, assuming that we pretend to be, rolling this 12 times, ideally 1 should appear twice, 2 should appear twice. In fact, all the numbers should appear twice, but that is not going to happen. Let us check this. 1 has appeared 5 times. 2 once, 4 once, 5, 2, 6, 3. And 3 has not at all appeared. And that is what is going to happen when we deal with random variable. But what about this probability? See, the probability of getting each and every number is said to be 0.16667. This is precisely what we are going to do. We are going to roll very large number of times this die, and we are expecting to get each number equal number of times. That can happen only when the number of times that we are going to roll is going to be very, very large. Still, the difference will be there. It will not happen that all the numbers we will get exactly same number of times. No, there will be difference. However, the difference will be insignificant going by the total number of times we are going to roll the die. So that is the idea behind this probability, right? So more or less it will be 3.5. It will not be exactly 3.5, and that is the difference in decimal, right? So let us start simulating that. So we did earlier, we are not going to adopt anything different. The approach will be same, but maybe there will be some syntactical differences because this time there are six numbers involved rather than only two. So let us go ahead and do this. We will create a data frame for this random variable, and we have written n as 10,000. So we are pretending that we are rolling this die 10,000 times. So let us create a data frame. We created a data frame. Let us see initial 5 records. This is how they appear. And then we have also done this dice dot index plus 1. Dice is the name of the data frame. So we are adding plus 1 to index so that the very first index number will be 1 and the last will be 10,000 rather than 9,999. We can directly use this index number for the calculation purpose rather than saying dice dot index plus 1. That is not needed. We have done once for all. Now see here what is going on. Since there are 6 numbers involved, when we are rolling the die, we will make note of what number we have got and we will put the count in that particular bucket. So if we are getting 1, the bucket 1 will be given the count as 1. When we get 2, we will put that count in the bucket called 2. So let us see how it is being done. Okay. Let us bring this line. So what is going on here? Just see the data frame. So what we have done here, look, these are random variables. First we got 5. So these are our buckets N1, N2, N3, N4, N5, N6, each representing the number pertaining to a die. So if it is 5, we will under this column write 1. We will take the count. If it is 2, under this N2, we will write 1. 6, under 6, we will write 1. 5, again 1. 3, 1. So on, so forth we will do. This is what this line is doing. So a dynamic query has been written to deal with 5 columns. Okay. We could have even written in a static manner, but it is fine. We have written dynamically so that one line will be good enough rather than writing 6 lines, we are writing 1 line. Okay. Second thing, what we are doing second, see, now let me come here and this time we will comment this. This has already been done, right? Now what we are doing, CS underscore N means cumulative sum for N1, then N2, then N3, then N4, then N5, then N6. Let us run and just see what's happened. We are calculating cumulative sum. So let us run this and we will discuss about this. Let us see the data frame. This is how our data frame looks. See here, 5 is 1, right? The cumulative sum for 5 is 1. Let us see when 5 comes next. Again 5 has come. The count we have already put here 1, 0, 0, 1. What is the cumulative sum? 2. It will become 2. Let us see. Now just see 2, 1, 1 and no other number is repeating. Okay, let us see some more record. 10 records we will see. Okay, see, let us see 2. See 2 here. Count is 1. Cumulative sum is 1. Next to, see here. Count is 1. Cumulative sum is 2. Again 2 has come. Count is 1. Cumulative sum is 3. This is what we are doing when we are talking about cumulative sum. So that is also done. Good. Now, let us bring the third line. What we are doing in the third line? Okay. We should be very careful while running this. Let me push this down further. Okay. Here. Now we will comment. This is done. This is also done. So this time what we are doing, let me run and then we can understand this. Dice. This is the data frame name. So EV1, EV2, EV3, 4, 5, 6. So what is that? EV means expected value. How will that come? So it is simple. We are dividing this cumulative N5 by 1. So we will get 1. Okay. Next time, what we have? Do we have 5? No, we have 2. But what has happened to EV5? Look, 1 is getting divided by 2 now, this time. Because look at this cumulative. Divide by 1, divide by 2, divide by 3. Correct? So we are getting under this 0.33. Then what happens? This count is going to increase. Why? Because 5, again we got 5. Now 5 has become 2. This 2 we are going to divide by 4. Then what we will get? We'll get zero point 0.5. So that is precisely what we are doing for each and every number, right? So this we did earlier as well. So once this line is executed, we have expected value for each and every number. Now, what we should be doing? We should go and see the last record. See, last record, how we can see? Let us see 5 records. The last one, just see, expected value for number 1, 0.166, 0.168, 0.1666, 0.162, 0.166, 0.169. See, when we started, this expected value was just see all 0, this is 1, then this became 0.5, this became 0.5, 0.3. So it wasn't uniform. But as the number of rolls increased, every number of the die is settling at its probability. What is the probability? 0.1666667. Correct? Now, if we say no, there is little bit of difference. How to avoid these differences? Well, that can be avoided by increasing the number of rolls that we know very well. So this has already happened. Okay. So now what we have to do? We have to create a graph. We will make a line chart and we will make line chart for all these expected values 1 to 6. So what we can do? We can now bring this up. See this stuff. Okay. Let me bring this up right here and just see what is going on here. We will draw the chart for first 100 rolls, then for initial 1000 rolls, and then for all the rolls. And what we are doing? Look, we are going to run this for each and every number 1, 2, 3. See, this is within the loop and this is a dynamic query. So first EV1 will come, then EV2 will come, then 3 will come, then 4 will come, 5 and 6, and we will get our chart ready. So what is this graph all about? What is this chart about? All about? This is for initial 100 rolls. And look, the line is going completely zigzag. But when we see for initial 1000, see this trend, which is this curve, which is oscillating too much, is settling at 0.16667. Look, still it is little bit wobbling. And now we will see for the entire set of roll. Like here, it has settled all the number 1 to 6 all have settled at 0.1667. Of course, there will be variation. Those variations can be taken care of by increasing the number of rolls. So having done this, what we should do? Look, we can easily remove all the things which we have used here only for the purpose of explanation. This was already written, so let me remove this. Let us unclutter this sheet. This is also not needed, not needed, not needed, not needed. Okay, we can see this and then we can see this graph. Okay, now let us calculate and try to get this piece. What is that? 3.5. How we will do? We have to EV1, this probability we will multiply by 1. This probability we will multiply by 2. This by 3, this by 4, this by 5, this by 6, and then we will add them up and we should get somewhere closer to 3.5. How we can do that? This graph we have already seen here. Let us remove this. So, what is happening? We are creating a list and that list is getting populated with EV1, EV2, EV3, EV4, EV5, EV6 so that we can only see we are from this data frame which is very wide, correct? Very wide. We are only looking at expected values for each and every number. Done. Now we will calculate the expected value. So what we are doing, just see, this is how we did manually. Now we will do through code. For I in range length EVs, what are these? EVs is nothing but a list. So first we will take EV1, then we will take EV2, then we will take EV3, 4, 5, 6. So that is what we are doing. We are taking EV1, right? What exactly we are taking? We are taking the last row. Just see when we are writing like this, dice lock, just see what is happening here. When we write this, what happens? Length dash is nothing but dash is 10K or whatever we wrote. This we are getting all the information about the last row. But what we are interested in, so if suppose if we are interested in EV1, then we will get, okay, EV1 is not defined. Why it is saying so? EV1 is defined, right? Look, this, 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 4, 5, and 6. So we will get 1 by 1 and then we will multiply by I plus 1. Why we are writing I plus 1? Because I will be 0 initially. So 0 is becoming 1, then 1, 2, like that. So eventually when we run this, we are going to get 3.5026. This is what is our expected value. Okay, so we can either get our E1, E2, E3 like this, or we did not write apostrophe, that is why we were getting error. So we have to write E not like this. This doesn't, I mean, it will give E is not defined. We have to write within quotes. If we get quotes, we will get this. And this is precisely what we are doing inside here. Okay, good. So we have also calculated through code the expected value of 3.5. What does this mean? This means that we calculated this manually, right? Earlier, this we wrote. And this calculation was based on the assumption that every number will have this probability. And through simulation, we created a scenario where we ended up getting the same expected probability. And then we are doing the same mathematical operation and getting this expected value. So let us see this whole Jupyter notebook. So here we are importing library. These are few lines of note, calculating expected value, then creating data frame like this, right? And then creating few charts to demonstrate how eventually the line gets straightened. In other words, each and every number settles at 0.16667. That is the probability for each and every number. Then we saw how we can slice and just see only expected values, and then we calculated the expected value using this small piece of code. And that's all. Thank you for watching, and I will see you in the next video.